Now that we've looked at min and max and find, let's talk about inserting and removing data from binary search trees. So we'll start off with the insert. So the insert actually is very similar to the find or contains operation that we've already looked at. It'll start by doing the find or contains. If it finds the item, great, it updates it or replaces it. And if not, it's stopped at a null, at a reference that could go to a new leaf, so we'll just add a new node or a new leaf. So let's practice a little bit. Let's go ahead and insert 16 into this tree. Okay, so again, we'll start with the search process. So we'll start at the root. 16 is after 11, so we'll go to the right. It's before 17, so we'll go to the left. It's after 15, so we would go to the right. This is a dead end, so let's just go ahead and insert a new node here with our 16. Okay. Okay, let's try another problem. Let's start with the same tree we had before, but this time we will insert 8 instead of 16. So same process as before. 8 is less than 11, go to the left. It's greater than 5, go to the right. It is less than 9, go to the left. It is greater than 7, we would try and go to the right, but there's nothing there. So we will create a new node and put our 8 in the new node. Okay. Insert is pretty straightforward based on the concept of finding a value. Now we'll look at the next method, or the successor method. The basic idea here is that we'll start at some node, x. So you'll notice that here all of the values of nodes are obscured, so we can think about the concept. So we'll start at some node x. And we want to find the value that comes after x, but as close to x as possible, so kind of the immediate successor value. Okay, so we can kind of rule out the left subtree, right? That's all stuff that comes before x. And if we go to the right, so this value immediately to x's right definitely comes after x, but we want to get the value that's as close to x as possible. So if we go to the left here, that would be a value that is less than this one to the right, but it still has to be greater than x because it's in x's right subtree. Okay, this illustrates one of the cases that we have for finding an in-order successor. So if we've got a right subtree, we'll take a right and then we'll go as far left as possible. So we want a value that comes after x, so we go to the right, but we want the smallest one possible, so we'll then go as far left as possible. Okay, that works if there is a subtree, a right subtree, but what if there's not? Okay, so let's consider a different problem. So this time our x is here, and it doesn't have a right subtree. So if we think about all of the values in the tree here, we know that the parent of x is less than x, right? Because x is to its right, is to its parent's right, so down this link. So we know that everything in the subtree is bigger than that parent. So obviously the parent itself can't be x's successor. But what about it? The parent's parent, the grandparent, so to speak. So in this case, we know that the subtree is somehow on a left subtree of the grandparent, and that's really the key here. Once you get to a point where you're on a left subtree of something, that first node that is kind of the branch to the left subtree, you know that first node there has got to be bigger than x. Okay, so really what we're trying to do is trying to find a subtree that somehow contains x on its left. And it turns out that there's a relatively straightforward way to do that. We can just traverse parents until the link from the parent happens to be a left-leaning link. Okay, so let's just practice that. So we'll do a couple of variations of next here. So next from the node containing 5. So this does have a right subtree. So we're in our first case, right and then left as far as possible to our 7. The value that comes immediately after 5 in this tree is 7. And just to kind of check our work here, yeah, 9, that's greater than 7, 11, 14, 15, 17, 20, 19, those are all greater than 7. So yeah, 7 is the value that would come immediately after 5. Okay, let's try another problem. This time, let's find the thing that comes after the node containing 15. Okay, this has no right subtree, so this falls into our second case. We're going to follow links up to parents until we enter a parent from where the connection from the parent to the child is on the left side of the parent. We did that immediately as soon as we got to 17. So the in-order successor of 15, the thing that would come next after 15, is the 17. Okay, let's try one more example problem. Let's find the successor from node 9 here. Again, there's no right subtree, so we will be in our second case. We will follow links up to parents until until the link from the parent to the subtree is on the parent's left side. Okay, so this particular link is on the parent's right side, so that's not of interest, so we'll continue up. And this particular link is on the parent's left side. So the successor of 9 would be 11. Okay, what if we want to go the opposite direction to find the previous node or the predecessor? Well, we could just reverse our concepts of left and right from what we did for the next or the successor function. Okay, moving along, let's think about remove. Let's imagine that we want to remove 2 from this tree. Well, first off, we have to find the 2. So we would go through our traditional find process. 2 is less than 11, we'll go to the 5, it's less than 5, we'll go to the 3, it's less than the 3, we'll go to the 2. We found what we were looking for. Okay, let's remove it. In this case, we could just go ahead and remove it, cut it off of our tree. That seemed pretty easy. Let's try another example. Let's try removing 9. So we'll start with our same initial tree, and this time we'll remove 9. Search process, we start at the 11. 9 is less than 11. We'll go to the left. It's greater than 5. We'll go to the right. Oh, there it is. We found our 9. Okay, if I just kind of try and cut off 9, that kind of leaves this hole here. But if we take the 7 and fill in that hole, we can have something that looks like this. That was pretty easy too. Okay, let's try another example. Let's go back to our original tree, and this time we'll remove 5, which is right here. Okay, so again, our find process would start at 11. You'd see that 5 is less than 11, so we'd move left and we'd find our 5. So before I just kind of cut off the node, but we can't really do that here. There are 2 subtrees. In the previous example, there was only one subtree, only one node that we really had to move up to do our replacement process. But this is a little bit more complicated. So instead what we want to do is we want to find what actually belongs in that spot. So imagine that we are going to remove 5. Is there something that we can somehow promote or move into this spot that would allow us to make the removal process a little bit easier? Okay, so just to kind of reflect on our findings so far, leaves were easy to remove, and even nodes with just one child were easy to remove. Those were our first 2 examples. But if the node has 2 children, that's kind of difficult to do. Okay, so let's not remove them. Let's instead swap around items so the thing that we want to remove ends up being one of our simple cases. It either has a single child or it's a leaf. Okay, so rather than trying to remove the nodes that have 2 children, let's swap them to some place where we can easily remove them. So instead we'll swap around items so the thing that we want to remove ends up having either 0 or 1 child, which makes it easy to remove. But if we're swapping things around, we need to make sure that that our tree is still going to maintain its order property. So we need to swap in the best possible value to maintain the order property and then do our removal process. Okay, so what would the best possible value be? Well, it would be the one that somehow ensures that the subtrees to the left and to the right are still valid, that the left subtree contains keys that are less than the newly swapped in value, and the right subtree contains values that are greater than the newly swapped in value. It turns out that the in-order successor is a perfect candidate for that. So let's go back to our example with removal of 5, and let's think about that. So to remove 5, it has 2 children. So we're going to do this swap process. We're going to swap 5 with its in-order successor. So again, we'll go through the process of finding the in-order successor. 5 has 2 children, so the in-order successor function will go to the right and then left as far as possible. So the in-order successor would be the number 7. So we will put a 7 there, a 5 there, and now where the 5 is at, it's easy to remove. And after kind of that two-step process, doing the swap and doing the removal, we have restored our order property. Okay, so we did our swap with the in-order successor, and then we do our removal now that the node that we want to remove is one of our 2 cases that's easy to deal with.